All right, so we didn't really talk with one another that are presenting here, but funny enough, a lot of the things I'm going to talk about today has been a little bit touched. I'm going to talk about all these topics from a little bit of a different side. My presentation is more a little bit about more a practical approach, what I see in the field when I troubleshoot, and how to detect these issues with the Ekahau toolkits. Because usually, oftentimes, first thing we try to do is reboot our devices, reboot the end clients, and if it still persists, Wi-Fi is not really touchable, it's not visible, so we need to make it visible, and with the tools we have on hand, we can really make our lives easier. Who in here has sat the ECSE design course? A lot of people, perfect. So one of the first slides in the course is this one here. A good configuration can fix a bad design. So this whole course is about how we can design a proper Wi-Fi. I'm gonna add my personal notes to this a little bit, because what I oftentimes see is a bad design, but on top of the bad design is even a worse configuration, and this makes everything even worse. So my take on this is a bad configuration makes a bad design even worse. And Wi-Fi is a quite resilient technology. So even if the design is not perfect, you can still make it work. Sometimes you have to play around with the rules of a proper design, and there might be good reasons to it. Sometimes you place an access point on the wall. We know it's not the best position. Oftentimes you want to have it on the ceiling. It's the proper propagation of the access point. The radiation pattern is made to do it like this. But even if you place an access point on the wall, it might work. So a couple of things I put in my presentations will show you improper designs that have even a worse configuration, and everything together make it completely break down. So let's see where it goes here. This is one of the slides from our ECSE troubleshooting course, where we basically try to provide a guideline or a flow chart how we go about troubleshooting. What's the first step when we do a Wi-Fi, when we try to design a Wi-Fi? First thing is always we define the requirements. And when we talk about troubleshooting, it's basically the same thing. We need to define a problem. And it sounds quite simple, but how often do you receive a call and it just says, Wi-Fi sucks, Wi-Fi doesn't work, internet is slow, whatever. It's not really a definition of the problem. It's what the end user feels, but it's really not showing you what's the real reason for it, right? So the big problem with IT guys like myself is we always try to start at the finish line. We try to mitigate the problem. We try to do something to fix it before we even know what the problem is, right? So we oftentimes try to take some shortcuts just to be able to fix issues before we know what it is. So it's oftentimes the definition of the problem that is like left out of the troubleshooting steps, and it takes a lot of time to really define a problem. So why it's important to do that is we need to know what the problem is before we can start capturing our data, analyzing the issue, and then analyze the data. And if we identify the issue, we can then do our remediation. This point here is a little bit misleading, because if you do not find the issue, you can't just stop. You need to look better, right? But this is like a circle until we have troubleshooted everything we have. This being said, my presentation today is more about the 4 issues I come across in the field most, and I'm going to show them to you. Hopefully it gives you a different way to look at certain rules and try to fix them. And funny enough, a lot of these points have been talked about today. So first thing, we're going to talk about the transmit power issues I see with transmit power. You will see it's not the way you think it is. The basic rates is always a big issue. A bad channel plan, that's what's covered by Matt and Mac before. And funny enough, the dual bond SSID is, I think, is the third presentation today where somebody talks about dual bond SSIDs. So, when I talk about transmit power or issues with transmit power, I don't think it's the way you think it is, or you think where I go, because it was Tobias that talked about the 18 dBm EIRP designs he sees mostly. In Ekahau, when you place your access points, it's a 14 dBm transmit power, almost 5 gigahertz per default. You can change these values to whatever you want. But the big issue is, in the end, when you start deploying your Wi-Fi environments with your vendors. How many of you use dynamic power selection or dynamic channel selection? It's a quite nice tool to save time or to not have to define it by yourself. But the big issue is all the vendors do it a little bit differently with the default values, right? So on the top here you can see this is from a Cisco controller. If you just use TPC in Cisco as default, it's anything between like 10 dBm and 30 dBm. The access points themselves, they aren't really able to go all the way down to like 10 dBm because this is 0.1 milliwatt, so they have like these power levels. But yeah, you will see oftentimes that if you leave it like this, access points will actually go down in power to the lowest level if they are not placed properly. Same thing with Extreme Networks or Aerohive, former Aerohive. They have like different minimum power levels, so 4 dBm, 5 dBm. Why might that be a problem, right? Because we are using dynamic power selection. The access point is making the decision, and we try to leave it up to the access point to make the decision. So the problem is improper AP placement. How many times have you, by yourself, placed access points in corridors? We know we try to avoid it, but in the end, sometimes it's unavoidable. So this example here on the left side, this is a long hallway with rooms onto the right side. I was called to this customer, the design was already made, they had placed around 500 access points, more or less like this. When we go back to my first slide, the best way to answer this would be, let's make a proper design. But they just did they did an installation, the design wasn't really made. 500 access points, every cable you pull is about £1,000, so $500,000 or pounds. You can try to ask them to move the access points, but in the end, they wanted to have a quick and dirty solution that it works, because what happened is they used dynamic power selection as well with Cisco, and access points are in a corridor. They see each other perfectly well. So AP1 sees AP2 and says, my next access point is right over there, so let's power down. I don't need to have my highest output power. Same thing happens with access point 2, 3, 4, and so on. So this is an extreme example, right? Same thing happens as well in areas like this here, where you have like an open space with multiple access points. If you place them on a ceiling, they see each other perfectly well, they power down. And if you don't configure the lowest output power, they oftentimes go to the lowest power possible, which is, in this case, it was, I think, the second lowest transmit power level, which was 5 dBm, about 3 milliwatts of transmit power. You can see this when you do an Ekahau survey and go into the inspect mode. If the access point, if the vendor gives us the information in the beacon frames, it also shows it to us inside the inspect mode in Ekahau. So the big problem here is people don't really work in the hallways. They work in the rooms, right? So right there where I put my X was the desk where they called me and told me they had performance issues. Not a big of a surprise for me. But the thing is really, so the placement of the AP, I'm not going to argue with you that this is a bad placement. But if we leave the configuration like this, it never gets better. We can fix this somewhat by changing the transmit power, right? Because what happened really is I did a packet capture right on the spot of the X, and I placed the client right next to it where they told me they had issues. And with Ekahau Capture, you can perfectly get all these data frames and analyze them in Wireshark. So if you're familiar with Wireshark, this is the I/O graph. I plotted the average transmit and receive basically speed from this client. So you can see that the red line is the downlink from all the data frames the access point sends to this client. But since the signal strength or the signal level on this spot there was so bad, they had to go all the way down to a MCS3 data rate around. So it wasn't really stable, right? You see it's all like squiggly lines. But it was about 58 megabit per second of data rates that were being used in the downlink communication. On the other hand, the uplink from the client to the access point was almost at the max MCS rate, so it was possible to go all the way up to MCS8. It was an AC access point. So you can see if the access point would use a proper data transmit power, they would be able to communicate with higher data rates. Oops. So best solution would be make a proper design, right? But in this case, 500 APs, they decided to wait a little bit. They needed to have money again, right? Because installation like this, a couple $1 million. So we were able to fix the issues by just changing these values here. We try to give guidelines to the access point so they can just go all the way down to the lowest possible rate or output power. And so when you read books like CWNA, stuff like this, everywhere you see talk about you need to make sure that the power level between access point and clients are aligned, or more or less aligned. But most of the times it goes into the don't use too much output power, right? But what I see in the field most of the time is the opposite, right? So access points go down with output power, and the downlink is impacted by this. And about 70–80% of my traffic that I see is downlink traffic. So I want to have a high-performing downlink. So for the next couple of issues I see oftentimes, I'm going to use the Ekahau Analyzer and AI Pro, so we can look at the issues on both sides. I was hoping to give you a small sneak peek with this screenshot here, but apparently the live demo already showed the nice new feature that we are going to have in Ekahau Analyzer, so the packet capture is going to be awesome. What Mac and Mac didn't really talk about to begin with is what this really does, what the Ekahau Analyzer really is built for. So on top, we can select any SSID that we can see within earshot that we want to try to analyze. So if you have multiple SSIDs, maybe you want to troubleshoot your office or enterprise SSID, or your voice SSID, or guest SSID, whatever. So you can click on the top there and select your SSID that you want to analyze. And how do we analyze our Wi-Fi networks? Our designs are always done against requirements we define, right? So when we want to analyze it, we also need to put in the requirements that we want to check. So the same thing applies here. They have some predefined RF requirements, but you can build your own individual requirement profile, where you can put stuff in like primary signal strength, secondary SNR. Everything that you put into Ekahau AI Pro, you can also put in here and validate your Wi-Fi environment against these requirements. And the next few bubbles are really just that. It's like a pass-fail ratio. Do we meet the requirements we put in regard to signal quality, channel quality, stuff like this? So, with that being said, so this is the first thing you need to do when you want to use your Analyzer app to analyze your Wi-Fi environments. So, first issue I talked about was transmit power. Second one is basic rates. This slide here, or this visualization, I'm not sure if you're familiar with this. If you want to have this it's available in an Excel format, so you can edit the values to your liking. This is from Andrew Van Nash. So just Google Revolution Wi-Fi SSID overhead calculator, and it provides you with an Excel sheet where you can put in your beacon size and how many SSIDs and access points you have within earshot on the same channel. And it shows you basically how much is the beacon overhead, just the beacon frames itself. So not a single client is connected to these access points, just the beacons, the 10 beacon frames per second per SSID. How much overhead does this generate, right? And as you can see, especially in 2.4, when we don't really address our basic rates, we will have 1 megabit per second as a default basic rate. And if you have 4 SSIDs on 4 access points within earshot, your RF environment is already over 50% utilized. This is the stuff you learn in your books, in your CWNA classes. I usually, in the beginning, you just accept it, but I wanted to see it with my own eyes, right? So I built my lab and replicated this in my lab. So I set up 2 access points with each what's that? Okay, with each 8 SSIDs. And as you can see, they're both on channel 11. And if we go in Ekahau Analyzer, we watch the channel quality. It actually gives us the RF utilization based on the spectrum analyzer inside from our sidekick. So again, this is what Matt and Mac talked about. It's the layer 1 information we are receiving here. How busy was the spectrum? When we click on the channel, we can really see more details and over time how busy the channel was. So even if you have just like some small spikes in utilization, we will see this inside our Analyzer app. How can we solve this high utilization? It's basically increase the minimum basic rate, right? The beacons are being sent out no matter what. So we can avoid having the beacon frames. We can reduce the number of beacon frames, but we can also increase the basic rates. And as you can see, I have 3 examples here. The one at the bottom, this is just for theoretical purposes, right? So you will never see or never do a basic rate of 54 megabits per second. It's just to show you how it affects the utilization. So again, the last row here, you can see the utilization from the RF spectrum analyzer is at 47% just by beaconing. It goes drastically down when I increase the basic rate to 24 megabits per second, and it decreases again. The next, the second to last row, this is the utilization that the access point tells us, how busy it sees our environment. So you can see, as Matt and Mac told us, it pretty much aligns perfectly between the layer 1 and the layer 2 utilization. But what happens when we reduce or if we increase our minimum basic rate? The theory tells us the The theory is the coverage area or the usable area of the access point gets decreased, right? I've done 3 times the same survey, same path. I scanned only one single channel, so I got about 2,500 measurement points for each survey. The theory should suggest that the higher the basic rates go, the smaller the coverage or the usable area. But as you can see, it seems like 54 megabits per second gives us a better coverage, right? Why is this visualization like this? It contradicts everything we know, right? The reason is we look at it from a wrong side. When we do a basic survey, the default visualization gives us an extrapolation or interpolation of 3 meters. So from the last measurement point we get in Ekahau, it assumes for 3 meters. It smooths the measurement points out. If you want to see the real data, what it gets us, we can switch it over and go to the inspector view. And what this really gives us is every single measurement point it takes us, it shows us individually. And here we can really see what's happening, right? When I had my basic rate at 1 megabits per second, I was receiving beacon frames all the way down in the outside area with the doors closed. When I increased the minimum basic rate to 24 megabits per second, I wasn't really able to decode the beacon frames when the signal level went too low. And 54 megabits per second, again, this is just to play around with the results to give you a better visualization of what happens. I wasn't really able to decode the beacon frames anymore. And that's basically what happens. And what we mean by increasing the minimum basic rate will decrease the coverage area. With 1 megabit per second, we will be able to decode our beacon frames even lower than -5 dBm. So the area where we can still decode the beacons is quite large. With 24 megabits per second basic rate, I was able, with my Sidekick, to decode the beacon frames to -82 dBm. And with 54 megabits per second, next 70 was the hard cutoff. I didn't get anything below this level. So that's really when we talk about increasing the minimum basic rate will decrease the coverage area. It will decrease the area where we can decode the beacons, right? Because the energy is still there, but we can't decode it because the modulation is just too complex. So basic rates is really oftentimes an issue where I see it when it's left on default, it's 1 megabit per second, and the congestion is just too high. When you want to edit it, usually you select something between 6 megabits, 12, or 24, but never higher. 24 is basically for high-density environments. So the second to last point here is, again, the part with the channel plan. It's funny, Matt and Mac talked about OBSS, right? Overlapping Basic Service Sets. My take here is a little bit different. Work with what you can, but do it right. These are access points that are not capable of using any channels other than Uni 1. So they were only capable of using channel 36, 40, 44, and 48. So we still have everything available up here to use, but not with these access points. So when we only have 4 channels available for our designs, don't use 40 megahertz channels. It's that simple. You only have 2 non-overlapping channels, and certain vendors still tend to have in their dynamic channel plans these differentiating primary channels, which will give us our OBSS and many problems, right? So this is where different primary channels, they don't play the game nicely, and they start to transmit at the same time, collisions, retransmissions, all the issues, right? So In this scenario, the only way to solve this would be replace access points that can use more channels, or at least stick to your 20 megahertz wide channels and never use alternating primary channels in 40 megahertz wide scenarios. When we want to analyze these channel health in Ekahau Analyzer, again, this is for our spot tests. So when we go just on site in one room and try to visualize how healthy is our environment, how healthy is our channel in there, and you can just go into the analyzer, channel quality, and it gives us all these nice colors again, red or green, based on the requirements we put into the analyzer app itself. And so the nice thing here is the same thing with our AI Pro. It not only gives us the co-channel interference where we have the same primary channels, it also gives us the information when there is some sort of OBSS overlap or ACI. We can, if you want to know what exactly is happening there, we can even dig into the channel, and it gives us the overview which access points within earshot are on these channels and causing overlap. All right, so we can mitigate this by just, in this case, changing the channels to use only 20 megahertz wide channels. So, and the last thing I really see oftentimes is, I think Tobias talked about this, that he sees this as the default setup right now. Matt and Mac talked about how they see this as an issue. And me personally, when I troubleshoot, I oftentimes see this as well, that dual bond SSIDs can cause quite the issues with performance and roaming. This device here that I grabbed the screenshot is an iPad, which basically prefers the 5 gigahertz band quite much. But for some reason, in this scenario, the iPad decided to switch onto 2.4 and stayed there. It's the same thing what Max saw. These devices, once they are connected on another frequency band or another access point, they tend to stick there as long as they're happy. But the performance is quite limited in the 2.4. One of my customers is a hospital with surgery rooms. They have like these video cameras. They basically take pictures and take videos of the whole surgery, and then afterwards they upload this onto the server. But the issue is these devices are not meant to roam. So once they, after the surgery, and they move this device outside of the surgery room, the device sticks to the 2.4 or connects to the 2.4 of this old access point and stays there. And their 2 gigabytes of data that they have to upload are going all over this 2.4 link. So as long as we have a dual band SSID, we can't really force clients to use or to select one or the other. It's just up to the client. And the big issue there is really we can't force clients to do anything. We can't try to use band steering, stuff like this, but then we start to mingle with roaming issues as well. So really these dual band SSIDs cause quite issues in performance-wise. And to analyze this as well, we can go into our Analyzer app and analyze the signal quality itself. And we can click through the different frequency bands, right? So 2.4, 5, and 6, and it shows us if our SSID that we are analyzing is in either of these bands, or if we select all, we can really see on one list if an SSID is on multiple frequency bands or not. And so the other way to look at this is really a great way. In the network overview of the analyzer, we can pull in our individual columns and visualize it different ways. So in this case, we can see I'm looking at my SSID, and we can see it's in 2.4 and in 5 using the different channels or different modes and generation of Wi-Fi. So these are really the things in the wild that I see the most. All these things cause, in my opinion, in the experiences I have, the most issues with the performances. And you make sure to avoid too low of a transmit power on the access point side and avoid dual bond SSIDs, as well as having a good channel plan. We're already halfway there, right? So I'm curious. I'd like to talk to a couple people of you, because I think everybody that does this presentation has a couple of different things. But as long as we try to stick to a good design and make sure that these things here work as well, everything should be well, and our Wi-Fi design and our Wi-Fi performance is just much better. And again, try to make sure the design is good, but it's not always possible, right? So oftentimes when we design our Wi-Fi environment, or if we troubleshoot the Wi-Fi environment that's designed by somebody else, the design is not always perfect, right? But we can work out certain configuration parameters to make sure that it at least performs the best it can, even in a bad environment. All right. Thank you.